Question 1 stated that at 12 midnight, while the temperature inside a house is 23 degrees Celsius and the outside temperature is -7 degrees Celsius, its furnace breaks down. Hours later, the temperature inside the house has fallen to 10 degrees Celsius. Assuming that the outside temperature remains at -7 degrees Celsius. For part 1a, we have to write the initial value problem mathematically and in differential equation form that satisfies the temperature inside the house after 12 midnight. First of all, we let T equal to the temperature inside the house at any time T. Then we know that dt over dt is proportional to T minus Tm, where Tm is the constant temperature. Then, we can rewrite it in the standard form where dt over dt is equal to K times T minus Tm. We know that Tm is equal to -7. So we will get dt over dt is equal to K times T plus 7. Next, we rearrange it and we integrate both sides. We integrate 1 over T minus 20 with respect to dt and integrate K with respect to dt. Then, we will get ln T plus 7 equal to Kt plus C. Then, we use logarithmic rule where e to the power of ln T plus 7 is equal to e to the power of Kt plus C. So, T plus 7 is equal to C e to the power of Kt. Thus, T is equal to C e to the power of Kt minus 7. Therefore, we can write it in the form of T of T, which is equal to C e to the power of Kt minus 7. For part B, we have to solve the initial value problem in A, that gives the temperature inside the house at any time T. When T equals to 0, then temperature equals to 23. After that, we use this value to equals to the general solution. Then, C e to the power of Kt is equals to 30. Thus, C equals to 30. Therefore T of T is 30, e to the power of Kt minus 7. When T equals to 2, temperature equals to 10. Then, let the T of T, which is 30, e to the power of 2K minus 7 equals to 10. Next, we get 30 e to the power of 2K equals to 17. E to the power of 2K will be equals to 17 over 30. Using logarithm rules, ln e to the power of 2K will be equals to ln 17 over 30. Then, 2K equals to ln 17 over 30. After some calculation, we get K equals to -0.28. We can write it back properly in the form of T of T equals to 30 e to the power of -0.28 T minus 7. For part C, determine at what time, when the temperature inside the house reaches 5 degrees Celsius. We let 5 equals to 30 e to the power of -0.28 T minus 7. Then, we will get 30 e to the power of -0.28 T equals to 12. Next, we divide the right hand side by 30. Using logarithmic rule, we get ln e to the power of -0.28 T is equal to ln 12 over 30. So, -0.28 T is equal to ln 12 over 30. So we will get T equal to ln 12 over 30 divided by -0.28. Thus, we get T is equal to 3.3 hours. The temperature inside the house reaches 5 degrees Celsius at 3:18 a.m. Question 2. A large tank contains 20,000 liters of pure water. Brine containing 5 kilograms of salt per liter is pumped into the tank at a rate of 20 liters per minute, and the well-mixed solution is pumped out at the same rate. Find the amount AT of salt, in kilograms, in the tank at time T. For the question 2, first thing first, let A of T be the amount of salt at any time T. Therefore, we know that d over dt is the rate amount of the leftover salt in the tank. We write it into the mathematical form where dA over dt is equal to Rn minus R out, where Rn is the rate amount of the salt that is pumped into the tank, while R out is the rate amount of the salt that is pumped out from the tank. To get Rn, we need to let the concentration of salt times the brine rate, where it is equal to 5 kilograms per liter, times 20 liters per minute, then it is equal to 100 kilograms per minute. For R out, it is equals to the concentration of salt times the brine, which is AFT over 20,000 kilograms per liter, times 20 liters per minute, where it is the same rate as Rn. Then, for R out, we get AFT over 1,000 kilograms per minute. Next, we substitute the value of Rn and R out into the first Roman equation, then we get dA over dt is equals to 100 minus AFT over 1000. We arrange the equation into the standard form of linear rho, dE, and we get dA over dt plus 1 over 1000 times AFT equals 100. Next step, we find the integrating factor for VFT. So from the equation, we get VFT equal to exponent t to the power of integrating PFT dt. Then we get VFT equals to derivatives of VFT times A equals to VFT times f of t. So, A is equals to 1 over VFT times integral VFT times f of t dt plus c. Since PFT equals to 1 over 1000, thus, from the equation VFT equals to exponent t to the power of integrating 1 over 1000 dt. Then we solve the integral, we get exponent e to the power of t over 1000. Then, by multiplying both sides of the differential equation by integrating factor, thus exponent e to the power of t over 1000 times a of t equal to the integral of 100 times exponent e to the power of t over 1000 dt. After solve the integral, then we get e to the power of t over 1000 times a of t is equal to 100,000 times exponent e to the power of t over 1000 plus c. Then we remove the exponent e to the power of t over 1000 on the left hand side by dividing both sides with exponent e to the power of t over 1000. Then we solve and simplify both sides and we get a of t equal to 100,000 plus c times e to the power of negative t over 1000. Then, we applying the initial condition, which is a of 0 equals to 0, then we get 0 equal to 100,000 plus c times exponent e to the power of negative 0 over 1000. Then after simplify we get 0 equals to 100,000 plus c times exponent to the power of 0. Thus we get c equal to negative 100,000. We substitute c in the equation A of t, then we get the answer amount of A of t of salt in kilograms in the tank, at t is equal to 100,000, minus 100,000 times exponent e to the power of negative t over 1000.